Hey, you've heard of Fermat's last theorem, right? You know, this thing that was unproven for 400 years? It's probably the most well-known problem on YouTube. If you're even remotely interested in math, you've probably seen some videos about it. You might know about Fermat doing a little trolling and saying he had a simple proof, or her wiles used some ridiculously technical argument to prove it. And these videos do a great job telling the history and key players in the story. Some of them even give a good overview of the proof itself. And if you're a little more curious, you might even look it up and read about it. But if you're like me, that's not quite enough. I mean, I want to hear it straight from the horse's mouth, you know? It's publicly available, so why not just look at it? Maybe there's no way to understand it, but you might as well see for yourself. So we stroll on over to Google and search for the proof. We don't want a summary, let's look for the real paper. Alright, here we go. Modular elliptic curves in Fermat's last theorem. Seems like an actual technical paper. It's in the annals. Alright, seems legit. Alright, now let's scroll down. Let's look for some real math. Alright. Galois representations. Okay. I don't know what that is. Let's just keep going. First theorem, here we go. For each prime, a representation. Alright, let's just keep looking. Representation. Why is this all about representations? Right, what even is a representation? In this video, we're going to try to answer that question with as little background as possible. There are no prerequisites, so there's not going to be any calculus or trigonometry or anything like that. To get started, we'll define a representation and then just break down each component separately. Let's just start off with the definition. This is a representation. Let's call it rho, this Greek letter in blue. A representation is a homomorphism from a group G to GLV, the general linear group over a vector space V. Now you're probably saying that all sounds like nonsense, and you're completely right. In fact, we don't even know what is G. What's this weird arrow? And what's GLV? But don't worry about all that. That'll be explained shortly enough. Let's start with groups. A group G is a set with an operation. Really, it's pretty simple. There's only two rules. The first is that the set has an identity. The identity under the operation does nothing to every element. And then the second rule is that every element has an inverse. So if I start with some element, there's a way for me to get back to the identity with its inverse. This is all still pretty abstract, but let's just look at an example to see how it works. Integers are a group. You know, 0, 1, 2, -7, 196,883. They're all integers which we denote z. These form a group because if we start at any element, say 2, we have the inverse -2, which takes us back to the identity 0. 0 is the identity because, of course, adding 0 does nothing to every other number. And it's important to note that we need both the set and the operation for a group. The integers with multiplication don't form a group because if we start at 2, there's no way to get back to the identity 1 multiplying by an integer. We would be trying to multiply by 1/2, but that's not in our original set, so that's not allowed. The integers are a group with addition because no matter where we start on the number line, we can jump around, go back and forth, and we'll always stay on the number line. Groups don't have to be infinite either. S3, the symmetric group on three things, is finite and actually pretty small. There are 3 factorial equals 6 ways to permute 3 things, and each permutation is an element in our group. Here they are. No matter what 3 things we have, we can always label them 1, 2, 3, and then these 6 arrangements are all of the possible ways we can order them. We can put together 2 permutations to get another one, but no matter what, we always stay in our set of 6 possible arrangements. Again, notice that we have the identity 1, 2, 3, which is the do-nothing permutation. It just keeps the 3 objects in the same order that we started with. Also, no matter what permutation we perform, we can always perform another one to get back where we started. For example, the permutation on the bottom left, 1, 3, 2, just swaps 2 and 3. So if we perform that permutation again, 2 and 3 will go back to the original starting location, and we'll be left with the identity. Now let's look at yet another group. GLV, that's right. GLV is called the general linear group over the vector space V. That's just a fancy way to say they're just matrices. And they look like this. Now, if you don't know what a matrix is, stick with me. It's just a bunch of numbers arranged in rows and columns, and we'll look at what they do in a second. The V in GLV just tells us what the numbers are allowed to be. In the matrices on the screen, the entries are all real numbers, so V would just be R. The only other case that we might encounter are the complex numbers, which are denoted C. Now, one more thing. These matrices aren't part of the same group because they have different dimensions. The one on the left is 2 by 2, and the other one is 3 by 3. GLV as a group only makes sense when we use invertible square matrices of the same size, so we'll specify this with a subscript. Alright, that was quite a lot about groups. Let's just take a break for a second before we continue. Now it's time for a crash course on matrices. Let's start with the xy plane shown on the screen. I'm sure you've seen it before. We're going to pick the simplest vector we can think of. It takes us one unit in the x direction, and that's it. We'll call it 1, 0, this red vector here. Now let's do the same, picking a blue vector that takes us one unit in the y direction. This is 0, 1. What we just did is called picking a basis, and in fact it's the standard basis. But never mind that, let's just look back at the xy plane. Let's say I want to get to this point up here. How do I do it? Well, I just draw a vector to it. Let's name it using the basis. To get there, we start at the origin and move one unit to the right, and then another unit to the right, using our red vectors. Now we need to move up, so we use our blue vectors to do this. It takes 3 blue vectors. We use 2 x vectors and 3 y vectors, so let's call our purple vector 2, 3. Our basis allows us to get anywhere we want just by adding the 2 simple x and y vectors that we created. Now let's imagine some transformation of the xy plane. This transformation just moves vectors around. So it takes our purple vector on the left to this purple vector on the right. We'll call this transformation T, and in fact, matrices describe how these transformations work. The matrix contains instructions for how to move in our new space. The first column tells us what happened to our red x basis vector. Instead of being 1, 0, now the red vector is -1, 1. And as you would expect, the other column tells us what happened to the blue vector. Instead of being 0, 1, it's now 0, -1. Now if you remember, we originally named the purple vector 2, 3 because it took 2 red vectors and 3 blue vectors. Let's see what happens if we combine 2 red vectors and 3 blue vectors the same way in our new space. It turns out that we get our purple vector, and the location of our purple vector is -2, -1. This is because matrices are linear transformations. Every vector is composed of basis vectors, so if I know what happened to our blue and red basis vectors I started with, then I can figure out what happened to any other vector under the transformation. In fact, this is encoded in matrix multiplication. When we multiply our starting vector by the transformation matrix on the left, we get the final vector. This isn't that important, but just remember, matrices tell us what happened to the basis vectors when we have a linear transformation. And if I know what happened to the basis vectors, then I know what happened to every other vector too. Let's look at one more group, the group Z mod 4Z. This is called a cyclic group and can be described as the set of integers mod 4. This means we can add and subtract any numbers we want, but whenever we get to 4, we cycle back to 0. For example, 2 plus 3 would normally be 5, but since we cycle back to 0 at 4, the answer is 1. This way, sums always add up to one of these 4 numbers. Also, you might be wondering what that squiggle on top of the equal sign means. For our purposes, it may as well just not be there. Whenever you see that symbol, just think equals or is the same as. Now it's time for a representation. But wait a minute, I haven't told you what that arrow means yet. Luckily, it's pretty simple. All it means is that a sum in our group turns into matrix multiplication in GL2R. For example, if I add 1 and 2, I get 3. Then, when I turn 3 into a matrix, I get the same thing as if I had turned 1 and 2 into matrices and multiplied them together. This is what defines a homomorphism, and it tells us that structure is preserved. When we map our group elements to matrices, the relationships between them are maintained. Now, again, I know this is all pretty abstract and we're moving very quickly, but we really have to work with an example to see what this looks like in practice. Here's our representation again. We're mapping our group to GL2R, which means that the matrices are 2 by 2 and have real entries. Row of 1 looks like this. Pretty simple, right? Now, let's think about what this transformation does. We're going to send our red basis vector to 0, 1, and we're going to send our blue basis vector to -1, 0. What results is this rotation, which is 90 degrees counterclockwise. Now, because of this being a homomorphism, this actually fully determines all the other matrices. The same way we'd add 1 twice to get the number 2, we can multiply the matrix for 1 by itself to get the representation for 2. In this way, we already know the representation of any number n. We simply take the matrix for 1 and multiply it by itself n times. What results is n 90-degree rotations of the plane for whatever our number n is. Now, if you're especially observant, this might sound familiar. Do we really need matrices to describe these rotations? Can't we just use complex numbers? And that's exactly right. We actually don't need matrices. It turns out that we can reduce this representation into a one-dimensional complex representation. This way, we're getting rid of the matrices and just working with complex numbers. We can replace the matrix for 1 with the complex number I, and we can replace the representation for n with the complex number I to the n via the same multiplication argument that we made before. This corresponds to a change in perspective of the plane. Rather than looking at it as the real xy plane, we can look at it as the complex plane, and we see that the group represents the rotations of the square centered at the origin. Rather than having this abstract view of the group with a set of numbers and addition mod 4, we get a much better geometric interpretation, which is the rotations of a square. Okay, now we have one representation under our belts. Let's try another one. Remember S3, the symmetries of 3 objects? Now we're going to look at S5. Let's say we cycle the objects like this. 1 goes where 3 was, and 2 and 3 shift down. We'll call this permutation 1, 3, 2. When we read from left to right, we say that 1 goes to 3, 3 goes to 2, and then 2 cycles back to 1. And because this notation is cyclic, we can move the numbers in order like this too to get equivalent views of the same permutation. Now, let's go back to the starting position. Rather than doing a cycle, we can get from start to finish by doing a couple of swaps. We start by swapping 1 and 3, and then we swap 2 and 3. This gets us to the same place, but rather than a 3 cycle, we have a product of 2 transpositions. And a transposition is just a fancy name for a swap. It turns out that every permutation can be broken down into a product of some number of transpositions. If the number of transpositions is odd, we call the permutation odd. And if there's an even number of transpositions, the permutation is even. Pretty simple, yeah? The permutation shown on the screen is even because it's the product of 2 transpositions. Now, we know that the group S5 has 5 factorial, or 120 permutations. As you might expect, half of them are odd and half of them are even. But if we think about it a little more, it turns out that these even permutations form a group. Why is that? Well, if we have an even number of transpositions and we add it to another even number of transpositions, we always get an even number, and that's not true for odd numbers. So if you put together a bunch of even permutations, you're going to get another even permutation, and this satisfies what we want in a group. We call this group of even permutations A5. A5 has many representations, but we're going to focus on a particular 3-dimensional one that we'll call kappa. This time we'll be mapping to matrices in 3 dimensions. Notice that we're allowing our entries to be complex. It turns out that sometimes using complex numbers instead of real numbers doesn't always reduce the dimension, but we won't get into that here. Instead, let's just look at some of the representations of specific elements. Our representation of the 3-cycle 3, 4, 5 looks like this. And yes, that phi is the golden ratio, and no, I'm not going to explain why. Another element just looks like this. Now, these look pretty similar, and it's because both matrices are rotation matrices. They're orthogonal and have determinant 1. This means basically that they only rotate space. They don't stretch, shrink, or distort it in any way. Also, notice that the element 3, 4, 5 is a 3 cycle. So when we map it to a matrix, we also get a matrix that has order 3. This means that taking it to the power of 3 turns it into the identity matrix. Likewise, the element 1, 2, 3, 4 just swaps 1 and 2 and swaps 3 and 4. So if we do it again, we want to get back to the identity. And this is reflected in the matrix representation of this element. When we square the matrix, we get the identity. But the real question is, what do these rotations do? What extra information does this give us? Do they represent the symmetries of some shape or object? The answer is yes. It turns out that they represent the rotational symmetries of a dodecahedron. That's right, this thing right here. Now, let me convince you. For starters, it better be true that there are 60 rotational symmetries of the dodecahedron. After all, A5 had 60 elements, so if they're the same thing, each element should match up to a rotation, right? Well, we can see this by looking at the rotations of the dodecahedron. We can rotate around each face 5 times like this. And we can also rotate around any of the 12 faces, so we get 60 possible rotations. But you still shouldn't be convinced. I mean, lots of groups have the same size, right? In fact, there are 13 different groups that all have 60 elements. Why should the rotations of a dodecahedron be the group A5 instead of one of any of the other 12 groups? If A5 is the group of even permutations of 5 things, then what are the 5 things? A dodecahedron has 12 faces, 20 vertices, 30 edges. How are we going to get 5 things out of that? Let's start with a cube. Now, you probably think I'm going insane. What does a cube have anything to do with the dodecahedron we were just talking about? But I promise, this is going somewhere. Let's throw in another cube, slightly skew, right on top of it. Okay, still nothing, right? Now, let's throw in a third one. And a fourth. I promise something will happen soon. Let's add the 5th cube. Now, maybe this looks like a colored, jumbled mess, but keep staring at it and see what happens. Do you see it? How about now? That's right. We can inscribe 5 cubes in the dodecahedron. Each cube has 12 edges, and we put them inside the dodecahedron by having each edge connect 2 opposite vertices on a pentagonal face. There are 5 ways to connect opposite edges of a pentagon, so we get 5 inscribed cubes that line up perfectly inside the dodecahedron. Let's take one more look at that. I don't know about you, but I think that's crazy. We looked at all the permutations of 5 objects, picked half of them, and got the symmetries of a platonic solid. How's that even possible? Let's take a breather. We just got through a lot of information. What did we get out of any of this? Well, we started out with some groups, which have pretty difficult and tedious computations. Group computations are hard. You know what's not hard? Matrices. They're easy to write down, simple to multiply, and there's fast algorithms for them all over. We even teach matrices and linear algebra to CS students, so you know it's not that bad. Representations help us get here. Groups also aren't very well understood. We can't even classify every group that exists. That's why we use representations. Matrices and vector spaces are very well understood. In some sense, we've already answered all of the important questions about them. That's a pretty convenient fact, and it's rarely true for any mathematical field. And then there's the fact that groups are algebraic, just symbols on paper. I know all of you visual learners out there don't like that, and representations take us to matrices, which sometimes have pretty nice geometric interpretations. Groups are also really hard to visualize. I mean, when at any point in this video, when I was talking about groups, did some image or picture pop into your head? Representations take us to matrices, which are easy to visualize. Okay, well, maybe they're not that easy, but they're not as hard as groups. Remember the square and the dodecahedron? In low dimensions, specifically 2 and 3 dimensions, we can get a pretty clear picture of what's going on. And look at this right here. This is how you write down the group A5 that we described earlier. What's better, that or this colorful platonic solid? Personally, I much prefer living in the matrix world where everything is nice and well behaved, and that's why we have representations. I want to emphasize the importance of this arrow here. I defined it once, but for the most part I sort of glossed over it, but it might be the most important thing in the whole video. The idea of mapping things to other things in mathematics is extremely powerful. It was the link between Diophantine equations and elliptic curves that led to the solution of Fermat's last theorem, and the Langlands program, the biggest project in modern mathematics, seeks to connect fields that previously appeared distinct, like automorphic forms and L functions. Whenever we have something difficult, it makes our lives a lot easier to map it to something else that's easier to work with. In some cases, the map itself is what illuminates the essence of two different domains. Representations are a vital instance of this concept, and we've barely touched the tip of the iceberg. You can spend the rest of your life working with them, but I hope this video at least gives you a better idea of what they are and why we should care about them. Thanks for watching. I'll leave some more resources in the description if you want to learn more, and if you like this video, please give it a thumbs up. It would really motivate me to make some more of these videos.